Hey everybody, it's me. We're going to look at equations of lines and planes in 3D space specifically, although, well, I mean planes in 3D, but we're going to talk a little bit about 2D. We'll start with lines. And as you remember in 2D space, if you want to just define a line, what you really need is you need some point that the line passes through, and then you need to have the direction that the line goes in. And we in 2D space, we need really a point and a slope. Those are like the two pieces. In 3D space, we'll similarly need a point, but really what we need with the point is a direction. And when I say direction, I really mean a direction in 3D. Nice thing is we already have a mathematical object that describes direction in 3D space, and that is the vector. So really we're going to have a point and a vector, which are going to be the two determining pieces that will give us a line. So given a point, so P0, which has coordinates x0, y0, z0, we also need a line that it's parallel to, or a vector it's parallel to. So vector v is the parallel vector, because remember, a vector doesn't have position, it just has direction. So really we want the same direction as vector v. Then we can write the equation for a line L would be r, the vector r, equals r0, the vector r0, plus t times vector v. Now for r, and remember r is the vector with coordinates x, y, z. So any point on the line will have coordinates x, y, z, which will be encoded into this vector r. We're thinking of the positional vector of the point x, y, z. And r0, the vector r0, would just be have the components x0, y0, z0. And then the vector v could be any directional vector. A, B, and C are its three components. So if we write this out, we can write this out using the notation. We can write x, y, z equals vector x0, y0, z0 plus t, scalar t, times vector a, b, c. Which if we distribute the scalar, we can write it like this, ta, tb, and tc being the three components. And then if we actually add the vectors all together, we can write it like this. So we have a vector x0 plus t times a, y0 plus t times b, and then z0 plus t times c. So that would be the components of this. Now if we were to write this, having the first component of r equal to the first component that we have on the right hand side, we actually get three scalar equations. X equals x0 plus ta, y equals y0 plus tb, and z equals z0 plus tc. These are called the scalar equations, I'll say the three scalar equations, and then this above is the vector equation of L. And it should be mentioned that t is just a real number, and t takes all values from negative infinity up to infinity in order to create all points on the line. So for our example, if we wanted to find the vector equation and the parametric equations of the line, or the scalar equations are also another word for the parametric equations, the scalar of the line passing through 5, 1, 3 parallel to this given vector, and then we can write this vector as the vector 1, 4, minus 2. This is my vector v. It would look like this. We'd have r equals, we'd have the vector 5, 1, 3 plus t times 1, 4, minus 2. The scalar, this would be the vector equation, and the parametric equations would be x equals 5 plus 1t, y equals 1 plus 4t, and z equals 3 minus 2t. So you can see where I get each of these. To form the first one, we take the 5 and the 1, and we have to put the t next, multiply the t to the 1. For the second equation, we have 1 and 4, so the 1 plus 4t, and then the last one we have 3 plus negative 2t. Now it should be mentioned that any vector that is parallel to v could be used to create the equation of the line. So the equation of the line is not unique. There's actually an infinite number. Any scalar multiple of v would work to give you all of the points in the line. But at any rate, this we would say this is like one vector equation that gives you the line that we're asked for here. So if we take the three parametric equations and solve for t, what we're going to get is three equations which are t equals x minus x0 over a. We have t equals y minus y0 over b, and t equals z minus z0 over c. And so we can actually set the right-hand sides all equal to each other, and we would write x minus x0 equals over a equals y minus y0 over b equals z minus z0 over c, assuming a, b, and c are non-zero. If any of these are 0, we can just set, so if a, b, or c are 0, we can just set the corresponding x, y, or z equal to x0, y0, or z0. But anyway, this is known as the symmetric equations of L. And there we go. So the symmetric equations of L, a concise way of describing a line in space. So now as an example, let's find the parametric and the symmetric equations for the line that passes through point A, which is 2, 4, minus 3, and B, which is at, so this is point A, this is B, 3, minus 1, 1. And these are just drawn randomly in space. Okay, that's pretty much what the line will look like. It doesn't really matter. To do this, what we need to do is take a point, and we can use the point 2, 4, minus 3 just as well as we could use the point B. But let's just use this as our point. And for the vector, we need to find a vector that goes from A to B. And so we're going to take the coordinates of B minus the coordinates of A. So we have 3 minus 2, minus 1 minus 4, and 1 minus minus 3. So this is going to give us 1 minus 5 and 4. This is our vector B. So the parametric equations are going to look like this. We'll have 2 plus 1t. So we take the 2 from the first coordinate of our point plus the first component of our vector times t. We'll have 4 minus 5t, and we're going to have negative 3 plus 4t. So those are the symmetric equations. I'm sorry. This is the parametric equations. The symmetric equations are going to look like this. Remember, it's x minus the x coordinate over the first component of our vector equals y minus 4, which is the coordinate for y, over the negative 5 equals z minus negative 3, which is actually a plus 3, I'll write it like that, over the 4. This is the symmetric equations, or these are the symmetric equations, I should say. But then we are asked for, we want to know when does sorry, I just had to fix the parametric equations. I forgot the x equals, y equals, and z equals. But then let's take a look at this second question, which is asking, where does this line intersect the xy plane? The xy plane is the same as z equals 0. So what we need to look at is, when does z equal 0? And z equals 0 precisely when, let's see, negative 3 plus 4t equals 0. And that, if you solve that for t, you're going to get t equals, it's going to be 3/4. So to find out when, what other coordinates you have there, we plug 3/4 in, And so the points are going to be 2 plus 3/4. We have 4 minus 5 times 3/4. And if you plug 3/4 in for the third coordinate, you get 0. And we can work that out. But let's at least try to like make it look a little nicer. So yeah, it comes out to be 11/4, 1/4, 0. Those are the x, y, and z coordinates of that point, where the intersection on the xy plane. One easy way to define a line segment and not a whole line is to just restrict the values of t, and oftentimes the simplest way to do that is just between 0 and 1. And so the line segment that goes from r0 to r1, which is to say, one point to another point, where the 2 points have position vectors r0 and r1, is given by this equation. So r of t is equal to 1 minus t times r0 plus t times r1. So you can see when t takes the value 0, you'll have 1 minus 0, that's 1 times r0, right, plus 0. So this goes from 1 minus 0 times r0 plus 0 times r1 to 1 minus 1 times r0 plus 1 times r1. The first one comes out to be simply r0, the next one comes to r1, and it'll be linearly interpolated between the two endpoints. Okay, so let's take a look at this example. Let's try to show that the two lines defined here, the first one, x equals 1 plus t, y equals minus 3t, and z equals 4 minus t. And the second line, where x is 2s, y equals 3 plus s, and then z equals negative 3 plus 4s. We want to show that these two lines both do not intersect and that they're not parallel. These are, These are called skew lines. Okay, so probably the first part is easiest, because the first is parallel to vector given by the coefficients of t, right? So the vector is 1, negative 3, negative 1, whereas the second is parallel to the vector 2, 1, 4. Okay, so the two lines are parallel to two different vectors, so they're not parallel to each other, right? So let's now try to figure out if the lines would intersect, what would t and s have to be equal to? That's what we have to do. And to figure that out, we just need to try to solve a system of equations where we set 1 plus t equals to 2s, we set negative 3t equal to 3 plus s, and 4 minus t equal to negative 3 plus 4s. And so in looking at this, the first what we can find is that t must be equal to, divide both sides by negative 3. It would have, you'd have minus 1/3 s minus 1. And if we were to plug this in for, let's take the other two equations and solve them for s. We would have the first one, s equals 1 plus t over 2. And the second one would be s equals, let's see, if we were going to add 7 to both, add 3 to both sides, we have plus 3 plus 3. So we're going to have 7 minus t equals 4s. We're going to have to divide both sides by 4. S is 7 minus t over 4. Okay, so if we were to plug in this expression for for t in both of these, what we're going to find is that we have an inconsistent system of equations. Let's take the first one. We'd have, plugging this in, we'd have, let's see, 1 plus negative 1/3 s minus 1 over 2, negative 1/6 s. The first equation is that s equals negative 1/6 s. The third equation, if we plug in negative 1/3 s minus 1, what we're going to get is, so it's 7 minus 1 minus 1/3 s, which is let's just put, if we put the 1/4 out, we have 7 minus 1 is the 6, so 6/4. And then minus, it would be 1/12 s. So the first equation, if s equals negative 1/6 s, that implies s equals 0. But if s equals 6/4 minus 1/12 s, well, I don't know, I'm not going to solve it exactly, but I know that that means s is not equal to 0. That won't solve this equation. So anyway, this is inconsistent. Sometimes because this system of equations cannot be solved by a single value of t and s, there's no point on either of the two lines where the two lines intersect. So to define the equation of a plane, we're going to need a point on the plane and a perpendicular vector, also known as a normal vector, also known as orthogonal. So we're going to call n the normal vector, and r0 is the position vector of the point, the one point that we have on the plane. So we kind of have this point, we have a normal vector, and then what we're doing is then defining the plane as all the points where all the points on the plane are going to be defined in this way. So to understand this, let's have the origin here, and let's put the equation. Let's draw I'm going to draw the position vector going to r0. Oops. And any arbitrary point on the plane will be vector r. If we were to draw the vector from r0 to r, any point from r0 to any point r on the plane, what we're going to be creating is a right angle with the vector n. And so we can define this in terms of dot product, which is to say the vector n dotted with the vector r minus r0, because it's orthogonal, a right angle, that dot product is equal to 0. And what we can do is actually we can distribute n dot r minus n dot r0 equals 0. And actually we can write it just as n dot r equals n dot r0. This is the equation of a plane. This is our vector equation of the plane. So we're going to use n, the vector n is the vector ABC, and the vector r0 is going to be x0, y0, z0, and r is equal to x, y, z. And so the dot product equation, the vector equation of the plane, can be written as this. So the first equation would come out to be a times x minus x0 plus b times y minus y0 plus c times z minus z0 equals 0. This is the scalar equation of the plane, as opposed to the vector equation of the plane. And n, we call it the normal vector, as I said. If we take the second form of the vector equation and expand the terms, we can write this. You notice that the first dot product is going to give you ax plus by plus cz, and then this next term is going to be, I'll put minus, and in parentheses I'll put the parts, which is going to be ax0 plus by0 plus cz0 equals 0. And what we write is ax plus by plus cz plus d equals 0, where d is just this this negative sum. This is just another equation. This is another linear equation in x, y, and z, which would also define a plane. Okay, so here's an example. We're going to find the equation of a plane through the point 2, 4, -1 with a normal vector of 2, 3, 4. And so this can be found, we're going to use the equation, the vector equation, which has the coefficients of 2, 3, and 4, of the coefficients from the normal vector. And we're going to put inside, we have x minus the x coordinate of the point. We have y minus the y coordinate. Oops. The x coordinate of the point is 2. We have y minus the 4, which is the y coordinate of the point, and we have z minus a negative 1, which would give us a plus 1 for the z coordinate of the point. And if we wanted to, of course, we can expand. We'd have 2x minus 4 plus 3y minus 12 plus 4z plus 4 equals 0. So we can collect the terms 2x plus 3y plus 4z. And then we have the minus 4 and the minus 12 and the plus 4, which altogether will have minus 12 equals 0. So either of these two are totally fine. These are two equivalent forms of the equation of this plane. Notice, so for planes, the equation, you have a single equation with essentially two degrees of freedom, or variables of freedom. If you were to set the values of x and y, then your value for z would be fixed. It would be determined. Whereas for lines, you had only one degree of freedom. Pick the value of x, and your values for y and z are both determined. It's a line is a one-dimensional object, whereas a plane is a two-dimensional object. Okay, here's another example. We have we want to find the equation of the plane that contains points p, q, and r. And so if you think about it in space, if this is p, this is q, and this is r, any 3 points will determine a plane. If we want to have the plane that contains these points, what we need actually still is we need a normal vector that sticks up like this, which would be normal to either of those two vectors, orthogonal to them. And that should make you think cross product. And that's exactly what we want to do. We want to, our normal vector is going to be PQ cross PR. And then the point that we choose could be P, Q, or R, either one of them. But really, we need to do this this cross product in order to find the normal vector. So let's find the vector PQ. We're going to need that. So the vector PQ is going to be the components of coordinates of Q minus the coordinates of P. So if 3 minus 1, we'll have negative 1 minus 3, and we have 6 minus 2. So this is 2, we have minus 4, and we have 4. Now our PR vector is going to be the coordinates of R minus the coordinates of P. So we have 5 minus 1, we have 2 minus 3, and we have 0 minus 2. And cleaning that up a little bit, we'll have 5 minus, that's 4, 2 minus 3 is negative 1, and 0 minus 2 is negative 2. So this cross product is going to be IJK, and then as the top row, remember we've got 2 minus 4, 4, and we'll have 4 minus 1 minus 2. So this cross product, if we do the I terms, that's the determinant of the submatrix minus 4, 4, minus 1, minus 2, minus the j vector times the determinant of the first column and the third column, which would be 2, 4, 4, minus 2, plus the k vector times this the first two columns, which is 2, minus 4, 4, and minus 1. So we're going to work this out. Actually, I'm going to just multiply these out, and so we have negative 4 minus 2. So remember, it's this product minus that product. So that's going to be 8 minus negative 4. This is going to be a 12. We have 2 and minus 2, so this is my plus, and then we have minus, so 2 minus 2, that's minus 4, and then we have minus, that's 4 times negative 4, which is minus 16, minus negative 16. That's actually going to be minus, another 12. And then we have 2 and times negative 1, that's negative 2, minus negative 16. That's going to be minus negative 16 plus 16. So that's going to be a 14. So I just realized I made a little mistake, so I have to go back and I put a negative sign in right here, which it is not negative, so I have to redo this a little bit. So notice what we have. We have 2, we have minus 2. So this is 2 times minus 2. I have to remember there's this plus, right? Or this minus right here. It's minus j times. We have 2 times minus 2 is minus 4. And 4 times 4 is 16 minus 16. But this is minus a minus 16, or minus a minus 20. So it comes out to be plus 20. So this normal vector should be 12, 20, 14. Okay, so there's my normal vector. This is my n. And I have the point r0 could be any one of these three. Let's just take p because it's the first one. And so my equation, my vector, the vector equation is going to be, we take the coefficients of n. We have 12x plus 20y plus 14z, and then we can put on the other side of the equation, we can have our the dot product of n 12, 20, 14 dotted with the 1, 3, 2, which if we work that out, we have 12 plus 60, that's 20 times 3, plus 28. So altogether that gives us 40, that's 100. And that's fine. We can if you wanted to clean it up a little bit, you can divide everything by 2. You could write 6x plus 10y plus 7z equals 50. That's probably the simplest way we could write this equation. So so there we go. That's an equation of this plane. So you had to find those two vectors, do a cross product to find the normal vector, and then you can put those into the equation for the plane. Here's another example. We want to find the angle between two planes. The first plane is x plus y plus z equals 1. The second plane, x minus 2y plus 3z equals 1. And so you can think of it like any two planes, as long as they're not parallel with each other, they're going to intersect at an angle. And so if you looked at sort of these two, like if you look at vectors along them, you'd have an angle between them, right? The angle between, but actually what's going to make a little more sense for us to think about is, in fact, if you take some point where the two planes intersect and look at the two normal vectors, one normal vector for one of the planes and say the other normal vector for the other one, which is say perpendicular to that one. If you look at the angle between those two normal vectors, that's the same as the angle between the planes. So that's what we're going to do to solve this problem. The two normal vectors can be found just by the coefficients of x, y, and z. The first one is just going to be 1, 1, 1. Oops, too many commas. 1, 1, 1. And the second one, the second normal vector, is 1, negative 2, 3. So how do you find the angle between two vectors? Remember, it's related to the dot product. The angle between two vectors is the cosine inverse of, it's going to be n1 dot n2 divided by the product of their two magnitudes. All right? And so we just have to evaluate that. What is n1 dot n2? Well, that is going to be 1 times 1 plus 1 times negative 2, I'll put in parentheses for multiplication, plus 1 times 3. Well, this is going to be 1 minus 2 plus 3. That comes out to be 2. Okay, the magnitude of n1 is the square root of 1 squared plus 1 squared plus 1 squared. That's the square root of 3. And n2, the magnitude of this vector, it's a square root of 1 squared plus negative 2 squared plus 3 squared. Let's continue that thing a little bit further. So this is the square root of what? 1 plus 4 plus 9. That's 14. Square root of 14. And so this is the cos inverse of, what do we have? 2 over the square root of 3 times 14, which is 42. You can work this out in the calculator. This is actually approximately equal to 72 degrees. So now if we were to try to find the equation for the line where the two planes intersect, then this is basically what we do. First we need to find a point, and we can just set any coordinate equal to 0. Let's set z equals 0. X plus y equals 1, and x minus 2y equals 1. We're going to try to solve these two equations and get our point. And so if x is going to be 1 minus y, so if x plus y equals 1, then x equals 1 minus y. We can plug that in. 1 minus y minus 2y equals 1. We can cancel 1 from both sides. And it turns out that y has to be equal to 0 as well. And if y is 0, then that implies that z has to be equal to 1, right? That's the only way. So the point is going to be 1, it implies x equals 1. So the point is 1, 0, 0. That's great. But we need a normal vector. And the normal vector, we need a vector for this line. And what we're going to use, the vector that's parallel is going to be the cross product of the two normal vectors. Because if you have two planes, so here's a picture of the two planes intersecting on a line, and I'll draw the line in red. Okay, so this line is going to be have a right angle between the two normal vectors. I'll try to draw the normal vector. The angle I'm drawing this is not very good, so I'm going to have to ask you to forgive me, but here's the idea. The normal vector to each plane is going to be perpendicular to this line. And so if you take a cross product of those two normal vectors, you're going to get a vector that is parallel to the line. So let's do that. So we're going to do what we did before, I, j, k. And we're going to have our two normal vectors, which remember, it was 1, 1, 1, and it was 1 minus 2, 3. So we have I times, we'll have I times 1 times 3, which is 3, minus 1 times, 1 times minus 2, which is minus 2. Minus j times 1 times 3 is 3, minus 1 times 1 is 1. Plus k times 1 times minus 2, which is minus 2, minus 1 times 1 is 1. So this is going to be, the vector is going to be written as a 5, minus a minus 2 is right there, and then we'll have minus 2 minus 1. We have minus 3. Okay, you can work that out a little slower. You could see exactly how that comes out. But we've done cross products a few times. I don't want to take too much time on the cross product. So we've got so if we have the point and we have this vector, we can write the equation. And the equation would be written x minus 1 over 5 equals z over negative 2 equals, well, x minus 1 over 5 equals y over negative 2 equals z over minus 3. Because the x and the y, because the y and the z coordinates are 0, we don't write anything in those numerators. So there you go. Those are the symmetric equations of that line. Really, it just comes from knowing what the point is and what the vector is, the parallel vector. Okay, so we want to find the distance between some point P1 and this plane and the distance is going to be an orthogonal distance. So we're going to, it's going to be the closest distance, right, to make a right angle. So if we were to, one way we can do this, right, so we can find, it takes some arbitrary point, I'll call it P0, that's on the plane. And if we were to draw a vector from P0 to P1, call that vector B. If we were to find the orthogonal, the projection, remember the normal vector, I'm going to draw it like right next to it because I don't want to go over the dotted lines. But if we were to take the projection of P0 of B and project it onto, it's not n1, sorry, it's just vector n, the normal vector. So the distance d is going to be the scalar projection of B onto n. And so let's write out so if P0 is just the point x0, y0, z0, I guess I'm writing it as a position vector. That's fine. I'm not going to worry too much about it. Actually, let's not confuse the notation too much. Let's write it using coordinates because it's a point. So P0 is x0, y0, z0. The vector B can be written x1 minus x0, y1 minus y0, z1 minus z0. And then if we were to find the scalar projection onto n, remember so d is going to be the magnitude of n dot b over the magnitude of n. This is the equation for the scalar projection of b onto n. You have to go back a few sections to review that, but this is the equation we want. So I'm going to do this dot product out in the numerator. So n dot b is going to, so I'm going to write it, write it all out. So n dot b, so remember n is, the vector n is a, b, c, right? So it's going to be x1 minus ax0 plus bx1 minus bx0 plus cz1 minus cz0. And then we have the magnitude of n is just the square root of a squared plus b squared plus c squared. That's a lot more straightforward. Now, if we go up in the numerator, we can collect the x1, the b1, the c1, ax1 plus by1 plus cz1. And remember earlier on, minus ax0 plus, minus by0 minus cz0, we define that as lowercase d. So we can actually have plus lowercase d over square root of a squared plus b squared plus c squared. This is the equation for the distance between a point and a plane. I'm gonna use this to just do one last example. So if we wanted to find the distance between two parallel planes given by these two equations, here's what we can do. We're going to first find a point on one of the planes. Let's find a point on the first plane. Let's set let's see, what's a good way to do this? Let's just set y equal to z equal to 0, and that means we have 10x equals 5. That means x is going to be 1/2. So we have the point 1/2, 0, 0. And then to find the distance between this point and the distance between that point and this other plane, we're going to use the equation that we just solved for. Okay, now remember, when we write out the equation like this, this over here, that would be negative d, because remember, we had the equation ax plus by plus cz plus d equals 0. So when we have lowercase d, if it's on the right-hand side, then that means d is going to be negative 1. As far as the a, b, and the c go, those are given by the coefficients of x, y, and z. So a is going to be 5, b is going to be the 1, and c is going to be negative 1. And then x1, y1, z1, well, those are just given by the points. So those are the points x1, y1, z1. So let's plug everything in. So we're going to have the absolute value of 5 times a half plus 1 times 0 plus negative 1 times 0. So we have to put in minus 1 times 0 and then plus d, which is minus 1. Okay, so then down below we have the square root of 5 squared plus 1 squared plus negative 1 squared. Okay, so up top we're going to have, so this is 5 halves minus 1 half, or 1, which is going to be 2 halves. And down below we have the square root of 27. Okay, so we have 3 halves times 1 over 3 root 3. So we can write that as 1 over 2 root 3 and be done with it. That's fine. I'm not so concerned with having irrational denominators. That's fine. So, all right, this was a long one. We covered a lot of stuff related to lines and planes and how the dot product and the cross product are used to help navigate those geometric objects. We'll do some more practice together in class. All right, bye.